Okay. Good evening, everyone. I am Marc Polanski, and tonight I'm going to show you 3 things to look for in the winter night sky that will be visible for the next few weeks. With the observatory closed to the public due to the pandemic, we know one of the things people miss the most is the opportunity to look through the various telescopes and see things in person. While this won't be quite the same experience as seeing the light from distant objects with your own eyes, it will hopefully give you an idea of what you could expect to see when we do reopen, or maybe through your own telescopes or binoculars at home. Here's a general overview of the sky right now, right about this time of night, facing south. Tonight, I'm going to focus on 3 objects that can be found without telescopes or binoculars, and show you what they might look like if you could look through a telescope, along with some pictures of what a camera could see of the same object. The 3 objects we'll take a look at are M45, better known as the Pleiades star cluster, M42, the Great Orion Nebula, and the planet Mars, which we'll hear more about from Bill a bit later on tonight. We'll start with the Pleiades, also known as the Seven Sisters or Subaru in Japanese. This is a great example of an open cluster, a group of stars that were formed at roughly the same time and are loosely held together by each other's gravity. The stars in this cluster look like a miniature version of the Big Dipper constellation and stand out for being a tight-knit group of stars that can be seen even with some light pollution. They're also fairly easy to spot when you're looking straight up, facing south at about 7 o'clock in the evening. This is what the Pleiades might look like through the Takahashi refractor telescope at the McCarthy Observatory. These stars are an average of 400 light years away from Earth, which means it takes about 400 years for the light produced in the stars to reach us. That's one of the most special things about seeing distant objects in space. We're really looking back in time by looking at these objects. What we're seeing is what the Pleiades looked like in the 17th century. It's also a relatively big object in terms of how much of the sky it takes up. If you can picture how big the full moon is in the sky, the Pleiades are about as wide as 3.5 full moons side by side. The big limitation we have as humans is that our eyes react to light in real time. This means as soon as light enters our eyes, signals are sent to our brain right away to let us know what we're looking at. Think of a faucet in a sink. Our eyes are like a drain, and the light is water coming out of the faucet. If the drain is open, the water flows right down the drain without really stopping. Our eyes do not have the ability to plug that drain and allow the light to fill up the sink. Fortunately, cameras can. A camera can collect light on its sensor for much longer than our eyes can. This lets the camera see much more of the faint or dim details of distant objects, especially when used with a telescope. This picture is about 60 seconds worth of light collected by a camera. You can see much more of the faint, wispy details between and around the stars than you could through the eyepiece. And there are far more stars, and they're much brighter in the background. This particular camera is black and white. It doesn't really see color, so I need to use filters to separate the colors so I can identify what it might really look like. When I combine all the filtered light, it looks something like this. The blue glow around the stars is from dust and gas, lit up by the brightest stars in the middle of the cluster. Here's a side-by-side view of what you might see with your eyes versus what the camera can see by collecting more light over time. With your eyes, the brighter stars and only some of the dust and gas are visible. The camera can see even more of the structure and some of the less illuminated parts, and even some subtle color differences between the blue and the grayish or reddish towards the bottom. The next object we'll look at is the Great Orion Nebula. The constellation Orion is relatively well known for the 3 stars in a row that make up the belt, making it fairly easy to find when looking southeast early in the evening. There are a wealth of objects to see hidden within the constellation, but the only one visible by eye is the Orion Nebula. You'll need fairly dark skies away from street or house lights to find this one. Look for the 3 stars of Orion's belt in the southeast sky around 7 o'clock. Just below the 3 stars, you may see a small fuzzy-looking patch with what look like tiny bright stars in the middle. That fuzzy patch is the nebula. Just like with the Pleiades, we'll start with an approximate eyepiece view. This is roughly what you would see if you were looking at the Orion Nebula through the 16-inch telescope at the McCarthy Observatory. The Orion Nebula is about 1,350 light years away, so this time we're looking even further into the past. It's about the width of 2 full moons in the sky. The 4 brighter stars just to the right of center are part of a structure known as the trapezium. There are actually 6 stars in the trapezium. 2 of the stars are smaller and can blend in with the larger stars, and it takes very clear skies and very stable seeing conditions with steady winds to be able to see all 6 of those stars separately. It's a very difficult thing to capture. Just like with the Pleiades, there's more to Orion than meets the eye. The nebula is a vast star nursery made up of huge amounts of gas waiting to form new stars and new planetary systems. The gases are energized by the stars in the trapezium, causing them to glow and light up the surrounding material. Once again, the camera is able to collect more light and show us some of the hidden details of the nebula you might miss with your eyes. And when imaged through color filters, we get a better idea of the different kinds of material that make up the nebula. Different gases produce different colors of light when energized by the stars within. Reds and pinks generally come from hydrogen, while blues and greens come from oxygen. It's easy to think of these things as two-dimensional, mostly because of our point of view being so far away. They just look like flat pictures. In reality, they're very complex, three-dimensional shapes that only look the way they do because of where Earth happens to sit within our solar system and where our solar system happens to sit within our galaxy. For instance, in this image, the darker brown areas are vast collections of dust that are not necessarily mixed in with the colorful gases, but rather in front of them. The brown material is in the foreground, the blue and gray are in the middle, and the reds and pinks are in the background. As you can kind of see, it has sort of a layered texture to it. Here's a much wider view of the entire constellation of Orion. The star Betelgeuse is the orange star towards the top, Rigel is the white star in the bottom right, and the 3 stars of the belt are just to the right of center. The Orion Nebula is the white and pink patch just below the belt. Also visible are the Rosette Nebula in the top left corner, and the Flame and the Horse Nebula in the center, or Horsehead Nebula, and Barnard's Loop, which is a large red C shape in the center made up of hydrogen gas. Last but not least is Mars. The red planet should be visible even in fairly light polluted skies. Look almost straight up while facing south around 7 o'clock in the evening, and you should see an orange dot not that far from the Pleiades star cluster. This time of year, Mars isn't the most exciting thing to look at through a telescope. Generally, it'll look like a bright orange star. At high magnification, in very good conditions, you may see some dark patches on the surface, but the best time to really see the details, like the polar ice caps, is when the planet is near opposition, or when Mars and Earth pass closest to each other as they both orbit the sun. Here's what I was able to capture with a camera last year in late September, about a week before opposition. The main benefit of using a camera with a telescope is the ability to collect more light from distant, faint objects. But because planets are so close compared to nebula and galaxies, the sun does a pretty good job of providing enough light that we don't need to collect light for very long at all. Instead, we can capture the light very, very quickly using video. By recording a video at 30 frames per second, it's basically the same as taking 30 pictures every second. If I record a 30-second video at 30 frames per second, I now have 900 pictures of Mars. That may seem like a lot, but there's a problem. This pesky little thing called the atmosphere. It's great for providing air for us to breathe, but it's terrible for taking pictures of things in space. The air and wind in the atmosphere make objects in space look like they're underwater with wobbling and shimmering. When you look up at the stars and they seem to twinkle, that twinkling is from unstable air in the upper atmosphere. Most of the time, this turbulence is random. There are brief moments of calm and tranquility where the details of a planet can shine through and be seen without distortion. If I'm lucky, out of those 900 pictures of the planet, maybe 50 or so will have those clear moments. I can then take those 50 good pictures and combine them together to create a best of composite image, showing off the details of the planet with as little interference from the atmosphere as possible. So thank you, and that's what's visible in the winter sky.